The olfactory sense, the sense of smell, is hugely important in many, many non-human organisms, even more so than it is in humans. So let's take a look at a couple examples. First of all, it's pretty undeveloped in most species of birds. There are a couple notable exceptions to that, and one of them is the Antarctic prion that we see here. They can detect odors of their mates. So the male goes off foraging for food for a couple weeks, and he's gone for a fairly long period of time finding food while his mate is back on the nest incubating. But when he comes back to the nest, he can actually locate which is his nest by identifying the odor of his mate, and it just aids in getting right back there really, really quickly, and probably strengthening the pair bond as well. This is another exception in the bird world of a species that's pretty good with odor. It's the crested auklet. There's a tangerine type odor that emanates from its neck. And both the male and female, these are males, that's one male and one female over there. I don't know which is which, they're identical. But in any event, they both produce the odor, and you'll often see them in courtship. Part of the courtship ritual is they'll bury their bills in each other's neck. Now, if we look at olfaction comparatively, jumping over to mammals now, humans don't have a whole lot of olfactory epithelium. That's the layer of cells in the upper portion of our nose that contain the olfactory or odor receptors, only 4 square centimeters. Despite that, we do pretty well in the realm of odor detection, but we pale next to other species. Even cats are better than we are. They have about 14 square centimeters, but among the champions, maybe not the champion, but just in terms of animals that we're used to having around us a lot, dogs have 150 square centimeters of olfactory epithelium. So they do quite well. Oh, that's me, and that's one of my former dogs. And that's me, by the way, when I was an undergraduate. So that was taken a long time ago. Okay, underwater sniffing. Sniffing for odors underwater. There are 2 species that do this really, really well. They have special adaptations that enable them to do this. The star-nosed mole, which we see here, that is actually throwing out air bubbles that it uses to engulf floating objects to see if they're edible or not. And the other one is the water shrew, which looks like that. We're not going to look at the water shrew. I just want to show you some clips of the star-nosed mole. So the air bubbles go out and then in. So right out of the head and back in, draws it back in as it's sampling objects in the water to see if from their odors they might be something edible. And you can see that they really use the bubbles. In one experiment, they put a screen between edible objects and the mole, and it's just able to detect whether it wants to eat something just by the air bubbles alone. It doesn't have to touch the objects, even though its paws are pretty incredible as well. Now, what you're looking at here is some wax. Let me point the wax out. I'll try to draw it out. Floating wax, okay, right there. Now, wax is not edible. So here comes our star-nosed mole that's going to put out air bubbles engulfing the wax, and you'll see that it's not the least bit interested in pursuing the wax as an edible object. So it just moves away from the wax. Here's a different angle. These are all slow motion, by the way. I think that's obvious. There's the wax. Here come the bubbles. And rejects the wax. Underwater sniffing. Just one more. The wax, the bubbles. Not a yummy item. Not going to eat it. Okay, now here's another experiment with a star-nosed mole. What they did was to take some earthworm extracts and put it down in this little area here. The mole is back in this area. They're going to release the mole, and watch how quickly, because the first version of this is in real time. Watch how quickly it can actually locate the odor of the earthworm. Here we go. Got it. Slow motion as it's sampling the environment. And it is throwing out the bubbles. You can't see all of them just based on the angle, but I think you can see most of them. There's some right there. And there, the earthworm odor. Similar experiment, that laser pointer is showing us where they've actually, where they're sort of diffusing some earthworm odor. Here comes the star-nosed mole, goes right over to it. Once it gets out of that starting area, can locate directionally where the odor's coming from. Then it goes home. Now they're going to shine the laser pointer over on the left, so that's where the odor is now coming from. Here comes the mole. Goes right over to where the odor is. Underwater scent tracking using these incredible air bubbles. That's what they look like if you take them out of water. That's the face. You're looking dead center at the face, and you can see where the bubbles are going to be coming out of its nostrils on either side, on both sides. And notice, yes, its claws are pretty prominent as well. A homunculus is actually a representation of areas of sensory and motor cortex on the surface of the brain. They've been drawn with humans a lot. Anyone that's had any kind of neuroscience background has seen pictures of the human homunculus. The relative size of the homunculus is based upon the amount of cortical control necessary for the different body parts. There's no size relationship here in terms of whether you have big paws or small paws. That doesn't mean you're going to necessarily have a larger homunculus if you have large paws. It's how much cortex is necessary to control or sense information coming from those areas of the body. And you can just see from this artist's rendition of the star-nosed mole how much cortex is devoted to controlling that facial area. It's quite enormous. Now, cockroaches are always cleaning their antennae, and it helps to improve olfaction because there are olfactory receptors there. Quite meticulous.
When they looked at the clean and the uncleaned antennae,
we very clearly saw a huge accumulation of junk on the surface of the antenna, and that junk is the cuticular hydrocarbons that are constantly excreted by the insect onto the surface.
These cuticular hydrocarbons are actually good in small doses.
They are absolutely critical for preventing water loss.
But too much of this waxy substance is bad. It clogs the pores on the hairs of the cockroach's antenna.
As you zoom in and look at these little hairs in very high magnification, you see this very smooth surface, and that smooth surface is the hydrocarbons occluding the cuticular pores that we should be seeing on the antenna.
And clogged pores aren't just a hygiene issue. Cockroaches use these pores to smell.
The cuticular pores serve to deliver the smell molecule into the inside of the hair, which contains the olfactory neurons.
And when the pores are gunked up with the cuticular hydrocarbons, the antennae weren't as receptive to scents, Scholl found, which may explain why the cockroaches are constantly grooming them.
So those are just a couple examples of non-human olfaction.